Hi guys, this tutorial is about electron probability clouds. So electrons, so far as we know, exist in energy levels. And you can kind of see in this drawing in the middle that neon, which is an atom in the noble gases, has 2 electrons in its inner shell and 8 electrons in its valence shell. And because it's a full atom, it is completely stable. Now, when you look at this drawing, it kind of feels like the electrons are orbiting around the nucleus like planets around the sun, but that's just because we're trying to draw a picture to make it easy to keep track of where our electrons are, because that makes it easy to show them bonding. However, I did tell you back when we first started talking about electrons that electrons are actually moving constantly like bugs around a light. And that's why I have on the right-hand side these bugs around a light to kind of illustrate the point that I'm trying to make. Even though they're not moving in this picture, it's a still picture, electrons really don't have to stay where you think they should stay. They have a certain amount of energy and they can get closer or further from the nucleus depending how much energy they have. But technically, they could be anywhere. What we're really trying to show when we put the electrons in energy levels is that they are most likely going to be found somewhere within this space. In other words, we're trying to show you where they'll probably be if you go looking for them. To help show you what I mean, we're going to draw a probability cloud for Mr. Stracuzzi. Mr. Stracuzzi and I live in this house at the corner of our street, and he works from home, and this window is where his office is. Now there's some other houses on our street, this one and this one and this one, and there's the local church over here. But another location that is of interest is this green awninged restaurant over here where my husband likes to go for lunch. And then there's this other place of interest, which is the local park where he likes to walk our dog. So what I want to do is I'm going to put a little tracker on my husband's phone, and every day for a year at exactly noon, I'm going to track where he is in the neighborhood, and I'm going to leave a little dot where he has been. Okay, here we go. So usually at noon, on the first day, let's say, he's right here in his office, he's still doing some work. And maybe the next day when I check in, he's actually decided it's time to take the dog for a walk, so he's just getting out the door. And then the next time he's over here in his office again, and then the next day he's a little further down the street walking the dog. And then the next day, let's say that he got an early start and he headed over to the pub early, and here he is at the local restaurant. Maybe, one day he gets going a little bit earlier than normal, and he's all the way over here at the park at noon. And I'm going to do this for 365 days, and the map's going to start to look like this. Sometimes he's over here, halfway to the park. Sometimes he's in his office. He's in his office a lot. He's doing a lot of work. Sometimes he's over here, getting a burger, going to the park, walking to the park. He's at the park. He's over here in his office doing some work. He's over here, getting a burger. And he's walking the dog. The dog's running all over the place. Oh, you know what? He decided he was going to go out of town for the day, and he's not home at all. Maybe he stopped into the church, see what was going on over there. Oh, he's visiting the neighbor. But most of the time he's at the park, or he's here, or he's over here. And at the end of the year, my map looks something like this. Now, what I have is a cloud that's shaped kind of like this. Whoop. That's the locations in the neighborhood where Mr. Stracuzzi is likely to be at noon on any given day. He'll probably be somewhere in that loop. He could be somewhere else. He could be all the way over here out of town. He could be over here visiting the church. He could be at the neighbor's house. He could really be anywhere at noon. He doesn't have to stay in this loop. But that's where he's likely to be if I go checking for him. This is exactly how electron probability clouds work. Okay, so let's make a probability cloud for our first 2 electrons around this atom. This atom has 10 protons, so he's going to attract 10 electrons. The name of this atom is actually neon, and neon, just so we're aware, has 2 electrons in the first shell. Oops, there's a 2 and 8 in the next shell. So we're going to figure out where these electrons actually are likely to be found. The first two are going to be found, if we were to take a picture, just like we did of Mr. Stracuzzi, of where they are every day at noon for a year, we would find that they would tend to be somewhere in this area. We couldn't really pin them down. They could go here, they could go there, they could go anywhere. But most of the time, they would be somewhere in this sphere. And because there's two of them and they're both negatively charged, they'll try and get as far apart from each other as they can. So probably one would be like here, the other one would be over here. They're not going to be right near each other. Even though we draw them that way when we draw neon. When we draw a Bohr model, we always put them together. And we do the same thing when we're trying to draw a Lewis diagram. We always put our electrons right next to each other. But technically speaking, they're always moving. They're not staying in any one place. They're not orbiting around on this line. This line here is the boundary of where they're likely to be found. So if we went looking for those two low energy electrons, they would be likely to be found very near the nucleus because they don't have enough energy to get away from that positive charge. Well, what about the next 8? Well, actually, we're going to look at them in pairs. The next 2 electrons have a little more energy, and we'll paint them red so that we can keep better track of them. So we can separate them from the blue electrons. So these electrons have a little bit more energy. So yeah, they could be in here. They could. But they are much more likely to be found a little further away. They've got more energy. So even though you might find a sprinkling of the occasional red inside the blue boundary, most of the time they'll be around here, just outside of it. And sometimes you'll find them over here and like all the way away. But in general, if we go looking for the next 2 electrons in the second level, they're likely to be somewhere in that sphere. Anywhere between the nucleus and that red boundary is where we'll find those next 2 electrons. And again, just like the first 2 blue ones, these 2 red ones are going to try and be as far apart as possible. So if this one happens to be over here, this one will go over here because they're both negatively charged and they repel each other. Now, I can't fit any more electrons in these areas. If I try and add more electrons, they're going to have to find places to go that don't cross paths with the other electrons. Because remember, they push apart from each other. So I'm going to add another layer of electrons. I'm going to make these green. The next 2 electrons are kind of like in a tough spot, right? They have a tendency to be, they have more energy. They have a tendency to be out here somewhere. But sometimes they'll also come down to the nucleus. And sometimes they go over to the other side and go down here. And again, they can be anywhere. They don't have to be in these exact places. But if we did this long enough, you'd begin to see it starts to take on a weird shape. It starts to look like this. The next 2 electrons in the second, this is still the second energy shell, we're here, are going to be somewhere in those figure 8 lobes. One might go into this one, and one would go into this one, so they can keep as far apart as possible. And you see how they're avoiding the other layers of electrons by doing this? Guess what? There's 2 more of those figure 8s. We've got 2 other electrons that'll hang out like this. Da-da-da-da-da, like so. And there's another pair, so one here and one here. There's another pair that actually would come in and out of the screen at you. So you kind of have to imagine one of these like, little figure 8s popping right out at your face and another one that goes back into the screen. I can't really draw it, so you kind of have to just picture it. You could take your pencil and just put your pencil right up against the nucleus. I wouldn't do the pointy end, I'd do the eraser end, and imagine that that's where you would see the part that's coming towards you. And that would have another 2 electrons in it. And this is why we had to follow that weird rule. When we do valence electrons, we put them in 1, 2 together, because those 2 actually are the red ones in the second energy shell, and they go together in that orbital. That's what that's called, an orbital. And then the next one would go here, that would be that one, and the next one would go here, it would be that one. The next one would go here, it would be that one. And then they start to double up. Another one can fit here, another one can fit here, and another one can fit here. So really, the top 2 electrons, the ones that I have circled, they are they're in a different shaped probability cloud, and that's why we treat them differently than the other 2. That's why we put them together 1, 2 on top, and then spread these out 3, 4, 5, 6, 7, 8. Okay, so now this is a professional drawing of the different probability clouds for an atom. So you've got the energy levels. This would be the first energy level right here, and that energy level can hold 2 electrons, and they tend to be somewhere inside of this sphere. We refer to this as an orbital. That's kind of an outdated term, but it stuck. Back in the early days when we first didn't know much about atoms, we kind of suspected that electrons would orbit the nucleus like planets around the sun, but we later discovered that wasn't true, but the name orbital stuck. So orbital is the word that we use for the electron probability cloud. It's shorter, so it has that going for it, but it's totally not correct. The 2 electrons, like I said, in energy level 1 are found inside of that small sphere. Then the higher level electrons that are found in the second energy level have these 4 different locations where they can go. We can put 2 in this slightly larger sphere, and we can put 2 each in these figure 8s. And that's how we get 8. And then this shows you all of them overlapping each other. So you've got the 1s, which is this sphere, the 2s, which is this sphere, and then you've got 3 p-shaped orbitals. I don't know why they're called p. S makes sense. That stands for sphere. I don't know what p stands for. They're figure 8s. 1, 2, 3 figure 8s. So you can see it kind of gets really messy. Now, if you're like me, you're probably wondering at this point, how did they figure this out? They actually did it with math. And I think it's really important to realize if you are interested in the sciences, get used to the idea that you're going to need to understand math, because this was all done with math, specifically with probability. So if you've ever learned anything about probability, like dice rolls and permutations and stuff like that in your math class, that's what you use that stuff for. It's actually a very practical form of math, and what they did was they actually calculated out mathematically where these electrons would be likely to be based on their attraction to the nucleus and their repulsion from each other. And that's how we get these interesting electron clouds. It actually gets even more interesting than all of that, and I hope that someday you will enjoy learning about it when you get to high school and beyond. And that's it for this enrichment tutorial.